Hi, multivariable calculus, Ms. Deer back on the mic. I just wanted to give you an introduction to the best theorem. That's right, I'm going to say it. Today's is the best theorem in all of the calculus, and it is Green's theorem. So George Green was an English mathematician, and he came up with this, and I'm going to say it to you in English. It says that the value of a double integral over a simply connected plane region R is determined by the value of a line integral around the boundary of R. Again, the value of a double integral over the plane in the region R is determined by the line integral around the boundary. So the theorem, the line integral around the boundary, that's this. And it is the same as a double integral over the plane region R of the partial of n with respect to x minus the partial of m with respect to y. So C must be traversed only once. So we're going to go around a region. We're going to go around it once, always keeping the region on our left. So think about, you always have your left hand on the region. And as long as I can find the area of this region in the xy plane, these are equivalent. So there's a beautiful proof of this in your book. I don't want to go into it too much, but I want to show you with an example of how this is going to work. So if I want to take, let's get a fresh piece of paper. I'm going to leave Green's theorem up here for your wonder. So let's say that I want to evaluate the line integral of y cubed dx plus 4x y squared dy. And I want to go along my curve is, let's do y equals x squared to 1, 1, and back along y equals x. All right, so I'm starting and ending in the same point. I have a closed curve. So if this field, my field is conservative, then it's not going to, I'm going to net nothing here, right? But that's not going to necessarily be true. So, and I'm not finding work, I'm just evaluating this line integral. So how much of this function is going to accumulate around this curve? So I could parameterize. So I could let r1 of t be t I hat plus t squared j hat, and then I could let r2 of t be 1 minus t I hat plus 1 minus t j hat. And I could parameterize each piece and figure out what I accumulate. Or I could use Green's theorem. And Green's theorem says that this line integral is equivalent to the double integral of the partial of n with respect to x minus the partial of m with respect to y dA. Well, where is n? So n is 4, what did I make it? 4xy squared. So the partial of n with respect to x is 4y squared. M is y cubed, so the partial of m with respect to y is 3y squared. So plugging these into here, I get the double integral over the region of dn dx minus dm dy dA. Now, as we know, because we are masters of the double integral, there are two different ways that we could write out this double integral. So 4y squared minus 3y squared is 1y squared. And I have dy dx, or I could do 1y squared dx dy. So if I look at dy dx first, my y values go from x squared to x my x values go from 0 to 1. Or in terms of dx dy, my x values go from y to rad y, and my y values go from 0 to 1. I'm not sure that either one of these is particularly easier to solve than the other one. So I get y cubed over 3 evaluated from x squared to x. So I get x cubed minus x to the 6 all over 3. Now I'm going to take the integral from 0 to 1. And this becomes x to the 4th over 12 minus x to the 7th over 3, which is 1/12 minus 1. Oh, this doesn't look right. Times 7 over 21. If I evaluate the other one, I get the integral from 0 to 1 of, then I have y squared x evaluated from y to rad y, which is y squared times rad y minus y. So I would take the integral from 0 to 1 of y to the 5/2 minus y to the 4/3 dy. This becomes y to the 7/2 over 7/2 minus y to the 4th over 4 evaluated from 0 to 1. So I get 2 over 7 minus 1 over 4. Are these the same thing? Absolutely. They both give you 1 over 28. So, I really want you to appreciate the value and the beauty of Green's theorem. We are going to talk about it in class. We can actually use Green's theorem to calculate work as long as I have a closed boundary. Again, on a conservative vector field, if I have a closed boundary, I'm not going to accumulate any work. So I definitely would not be needing to use Green's theorem on a conservative vector field to find work. So I want you to read through section 15.4 in your textbook, and then we will do some examples live in class. Best theorem ever.